Number 19, integral from 2 to infinity, x squared plus 4x plus 4 over square root of x minus 1 quantity cubed times square root of x cubed minus 1 dx. This is a crazy function. You probably want to think of a comparison test. Okay, but why is it improper, first of all? Well, clearly this upper limit is infinite. Do we have to worry about any discontinuity? It's discontinuous when x is equal to 1. Okay, but we're outside of that region, so we're okay. There's a domain that x has to be x cubed minus 1 has to be greater than 0, greater than equal to 0. We can't divide by 0, so greater than 0. So again, x would have to be greater than 1, which we are. Okay, so we don't have to worry about any discontinuity in this case. Okay, so if you've been following along in this series, I've been saying we should have some intuition as to whether this function converges or not. Okay, so this is how we think about it. As x approaches infinity, our function, it's like taking the limit. Let's worry about the top first. Which term would dominate as x keeps growing or as x keeps approaching infinity? The x squared term would dominate. Imagine x to the 10, or x is 10 billion. 10 billion squared plus 4 times 10 billion plus 4. That 4 is so insignificant. And 10 billion squared, this 40 billion is quite insignificant as well. So you can see as x keeps growing even more, these lower degree terms will be insignificant. So let's just keep the x squared, okay? Similarly, on the bottom, the square root of x would keep growing much faster than this constant of 1. So we just keep the square root of x and don't forget the cubed. And similarly over here, the cube root will grow so much faster than this 1. So we keep just the cube root, but under the square root, okay? We start simplifying. This would equal to x squared over x cubed, which is 1 over x. So this function will actually behave very similarly to 1 over x as x approaches infinity. Okay, so it's likely going to diverge because we know the integral from 1 to infinity, or 2 to infinity even, 1 over x dx diverges. 2 because our limit over here is 2. Okay, 1 is fine as well. Okay, so if you've been following along in this series and you've noticed some of the comments in some of my quote-unquote more controversial videos, I am doing a direct comparison test here. I'm not doing what some people call the asymptotic comparison test because, to be honest, I've never met a student in my real life where they learned about some asymptotic comparison test during this improper integral section. If you think about it, whatever they're talking about, that asymptotic comparison test is really the limit comparison test if you know about infinite series and you're watching this because you're just curious about what the solution is to this, or you're watching it for fun, I don't know. But if you know about the limit comparison test in infinite series, that's actually what they're talking about. But most people don't learn about the limit comparison test during the improper integral section. So that's why I'm not explaining that, or I'm not just saying, oh, it behaves like 1 over x and we're done. If you're taking this class and your teacher did not teach you, or your teacher, professor, whoever, did not teach you about this limit comparison test, you might get marked off. Okay, so that's why I'm talking about the direct comparison test here, in which most students learn. Okay, enough rambling from me about that and trying to defend myself per se. But anyway, so I'm going to set up a comparison test. We're going to use this intuition to help us out. We're not doing the limit comparison test, but we're going to use the kind of results per se of the limit comparison test to help us set up the direct comparison test, okay? So for x is greater than or equal to 2, okay? This is our original function, okay? Hopefully you would agree that it's greater than or equal to, I just touched the bottom over here, okay? X cubed times the square root of x cubed, or square root of x, quantity cubed, times square root of x cubed. That's hard to say, okay? Which if we simplify is equal to x cubed on the bottom. This is the exact same thing, actually. If you remember, you can rewrite these in different ways. You can write this as this, or you can write this as this over here. Just properties of radicals, which are properties of exponents, actually. Okay. So I set this up, and actually, before that, at least for me, it's really hard to show that our function is actually greater than or equal to 1 over x. If it is, I don't even know, to be honest, right now, off the top of my head. It's really hard to show. And that's why I would not choose to do it for a direct comparison test. say that this guy is greater than or equal to 1 over x. Okay, and this is where I got lots of criticism in my other videos because sometimes it actually wasn't true, but then they were so stuck on the limit comparison test as the result. But anyway, so hopefully you get my points if you came from those videos. Okay, I'm doing the direct comparison test, and it's hard to show that this guy is greater than or equal to this guy if it's even true. Again, I don't even know. So I'm going to pick a different function to be safe. Okay, and I picked this guy, which is equal to this guy. This we can evaluate the improper integral of. We can just divide through by the x cubed. And you can see the 1 over x appears, finally. Okay? And I showed the work, but we already know that this guy would diverge, but these two would converge actually. So it doesn't matter that these two converge over here because this one diverges, the whole thing diverges. Okay? And therefore, since our function's even bigger than this guy that diverged, our guy diverges as well. Okay, that's how I approach this problem. Again, with a direct comparison test, not the limit comparison test, or asymptotic comparison test, some people call it.